Hello. Hello. Hmm. Good. Thank you for joining, guys. Today we are going to study linear regression, technique in machine learning, through a very simple basic example. So what we are trying to understand is that we already know that there are some libraries, pre-built libraries that are built on top of numpy. For example, scikit-learn library is there. So through that we can implement, we can use linear regression for any regression problem, right? But today we are going to understand like how are these algorithms, or like behind the hood, like how are these libraries are built on top of numpy. So today we are only focusing on linear regression, um, and I'm going to collaborate with my fellow learners in the course of IIT Delhi that I'm pursuing currently. So I'm waiting for my fellow learners to join. The timing is 8:30. Sorry for keep you waiting. You can skip ahead to get to the original content. Okay. This is going to be the public video, so anybody can access. No problem at all. I'm going to wait for some time for my fellow learners to join in this session. Again, thank you for waiting, guys. We will start soon.
Hi. And thanks you because due to you I'm learning. Mhm. Okay. Okay. Thank you. No, no. I have really, you are teaching very well. I have one question. Can I ask you? Is it the target means labor, right? Okay. 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 Thank you. Oh, okay. Thank you. Yeah. Yeah. You can move.
Okay, okay. Actually, I've made a mistake. I have muted on the YouTube video, so they were not able to listen what I was saying so far. I'm sorry, guys. I was not able to. That was my mistake. I forgot to unmute on the video. Uh, it's okay. I'll share this notebook, guys. You can go through the notebook. I have already said what is about linear regression, and it is already written in this notebook. You can go through. I have only go through the 4 and 5 cells only. I have not executed any code so far. So from here onwards I will start with the linear regression. Okay, so what we are trying to model a function for linear regression with one variable, and this is our problem statement that we wants to solve using linear regression. Okay, what we are trying to do is, let's say we have an input feature, that is the size of the house, and we have the output target, that is the price of the house. Okay, and the size and the scale of the size of the house is in the 1,000 square feet, and the scale of the price of the house in the thousands of dollars, correct? So so our training data, I'm only taking two data points for the simplicity of the algorithm. We can use multiple thousands of data points as well, no issues, but for the simplicity we are doing it. So I have this data set where 1,000 square feet of house, this is the training set that we are providing to the algorithm, that is, this is the actual price. The You can say that the 1,000 square feet of house was recently sold for $300,000, and we have another data point, that is 2,000 square feet of house was recently sold for $500,000. We have this data set, and through this data set we are going to create a linear regression model. So how we will create the linear regression model? We will give this data set to our learning algorithm, and the learning algorithm will produce a function, and the function will be helpful for us to predict the new output based on the new feature or new input. So let's say if I want to predict what will be the price of the house of let's say 1.5 1,500 square feet, that data we do not have here, but as we will create this function, we will be able to predict the price of the house. Okay, I'm sorry, guys. I forgot to unmute myself. I keep talking, but that is okay. If you have any questions, you can paste it in the comments, and I will answer each of your question regarding this linear regression using numpy. Okay, no issues. Uh, okay, so now we have come to the mathematical part. Now we have the problem statement. Are we clear on this problem statement, Simran? Are we clear on this problem statement? What is the problem statement and how are we going to do it?
Yeah.
Okay. Can you quickly just tell our viewers that what we are going to do, so that I can also know that I am explaining it well, if you don't mind, and I can repeat if you don't mind. That is fine.
I think you explained very well. But okay, in this problem, we are predicting the price. It's a very good model, linear regression, to help us to predict our new things. So in this example, we are predicting the house price.
Yeah, that is absolutely correct. Mm-hmm. And how are we doing it? We are giving the training data set, right? We are giving the
Yeah, we
training.
are giving.
Hmm.
Is it possible? Can we do the also the validations as well for training, testing, and validations data
Yes,
as well?
yes.
So
In the real case scenario, what we do is we split the data set into 80 and 20% ratio.
yeah,
Okay, so 80% will be the training set and 20% will be the validation set.
I think the 80% is the training set, and the if we say ki we are dividing, but I think 20% is a testing set,
Yeah,
right?
testing set, correct. Hmm.
Mm.
Right.
Okay.
Right. So that's what we are going to do. Now I'm going to import numpy library. That's the code for importing the numpy library. This is the meaning of the first line, and the second line is the matplotlib, and I'm going to import the matplotlib as well. So matplotlib is the plotting is the library used to plot the data. Okay, see, it has been imported. Now the next thing is what we are going to do. We are going to create our training set xtrain, and xtrain is the numpy np.array in which there are two data points. So we are creating the numpy array with two data points, and we call this xtrain. Also we are creating the ytrain variable, a ytrain. We are creating another array which represents the price of the data point, which is 300 and 500. These are corresponding to the value of the x train. So in the real case scenario, guys, what we do is we import the data from some data format, let's say CSV file, Parquet file. There are many types of file through which we get the data. But eventually what we do is we create the numpy array out of those data frames. Right? As I said, we are going to implement using the numpy only. So for that purpose, I have created this input feature xtrain. Okay, this is the input feature. Okay, input feature with two data points. Okay, correct. And this is the output target with corresponding value. Okay, and together this will be called as training data set. Okay, use m to denote the number of training examples. Oh, so what is the m here? M is 2. Now let's check the shape of the x train, and m is the number of the data points. Now this is the print statement which will tell the number of the training example. I'll run this cell, and I can tell that x train has 2 comma 2 comma 1 2 comma 0 of shape, yani two data points are there, and number of the training example is 2. That is only two data points we are considering for the simplicity. Okay, training example XI YI. You know what do I mean by XI? You will use XI superscript XI comma YI to denote the ith training example. So since Python is 0 index, we can say x0 comma y0 is 1 comma 0 comma 300 comma 1 comma 0 comma 300, 1 comma 300, 1.0 comma 300. This is the first data point, and this is the second data point x1 comma y1, 2 comma 500. So to access a value in numpy array, one indexes the array with the desired offset. For example, the syntax to access the location of 0, we will use xstring 0. If I print xstring 0, it will give me the value of 1.0, correct? Okay, now we are plotting the data using scatter function, which is provided by the matplotlib library. Again guys, we are not using this matplot library to implement our model. We are using this matplot library to visualize our data set. Here I have written the code to plot our data points. As you can see, let me run this cell. As you can see, we have two data points. One is here, that is one house is sold for 1000 square feet. One house of 1000 square feet was sold for $300,000, and another house of 2,000 square feet was sold for $500,000. So we have two data points. Okay. As described above, the model function for the linear regression is represented as fwb of xi is equals to में wxi plus b. The formula above is how you can represent straight lines. Different value of w and b give you different straight lines on the plot. Let's try to get a better intuition for this through the code. Let's start with the value of w is equals to 100 and b is equals to 100. Here w is the weight and b is the bias, and in the context of straight line, w is the slope of the line and b is the y-intercept of the line. So we are considering w and b 100 and 100. We are just taking the random example here. Okay, but our goal is to find the right WB so that our model will fit well. Our model will fit our training data set. The model will generate the value of W and B eventually. Correct? This is what we are trying to do. The purpose of applying the algorithm is to get the values of W and B, so that we will be able to create the straight line, and through the straight line equation we will be able to predict the value of new input feature. Now let's compute the value of WBXI for your two data point. You can explicitly write this out for each data point as x0. WFB is equals to में W into में x0 plus b. Here what does it mean? That this function W, this function f fits this particular data point. Yani x0, and it will give us the value of y0. Okay, for x1 fwb is equals to w into x1 plus b. For a large number of data point, this can get unwieldy and repetitive. So instead, you can calculate the function output in a for loop shown in the compute model output function below. Okay, I'm computing the function here. Okay, I'm defining this function compute model output. Here I'm providing the x input features. Here x is the numpy array. Again, x is the numpy array. What do I mean by numpy array? X is this 1, 0, 1, 2, right? So I'm providing x and I'm providing w and b, which I have taken as our example for guessing. We'll proceed with creating the algorithm, but first we are trying to create the intuition of the function itself. Now what does this function does? Okay guys, so this is how you define a function in Python. This is called docstring. In the docstring we are defining the function purpose. Okay, the function computes the prediction of linear model. It takes the argument x and the array of m examples and w and b some scalar values, yani ki model parameters. And what does it return? It will return the function itself, model prediction. What is the model prediction? It will return that. Simply it will return that. Right? And now you can see we are simply going through the, I think this should be the plus if I am not wrong. I think this should be the plus. Okay, let's run this, then we'll check. We have defined this function and it will return the function fwb. No, this is the function. Yeah. Now let's call the compute model output function and plot the output. Now I'm defining this temporary fwb and I'm calling this function based on our input dataset xtrain, input features xtrain and w and b parameters. This is what this function needs. One nd array, xtrain and model parameters w and b. Now let's compute this model. Now I have plotted this model on this graph. Now if you see, the model is inaccurate. Can you see? Can you spot why it is inaccurate, Simran? Why the model is inaccurate here?
Because of straight line, but it's the outliers I'm looking here because of due to value.
Yes, correct. Because it is supposed to cross this data points, but it is way too far from the data points.
Yeah, that's why I'm asking. It's the outliers.
Yes, correct. So the model is inaccurate. What does it mean model is inaccurate? Yani ki W and B does not result in a straight line that fits out our data. Correct. Now let's try with something else. Now I'm trying with 200 and 100. Okay, another W and B. I'm guessing now. Okay, I did nothing different, just this. Okay, fine. I'm plotting this. Now, can you see what difference? What is the difference? And here, our model is ready to predict the output of target variable. Why? Because it is fitting the data set really well. You can see it is crossing the data points correctly. The function is fitting the data set really well. So if let's say this is the source of truth, the training set, and now if I give a new value, 1.2, that was our initial use case, it will be able to predict the value of my house well. Why? Because the model is fitting the dataset really well. So what we understand so far is W and B are the parameters of the model that we really want to find out. Correct? Correct, Simran? We want to find out the parameters, and as This is only two data points and I already know what is the right value. So that's why I was able to predict this. But this trial and error way is not optimal solution, correct? So here comes, are we right? This trial and error way is not the optimal solution. How long will you keep doing it?
Yeah.
So here comes the optimization algorithm that helps us to find the model parameters. Some optimization algorithm will come into play that will help us to find the model parameters. And this algorithm is known as, and one of the algorithm that we are going to learn today is known as gradient descent. So with the help of the gradient descent, our model will be able to find the values of W and B. And once we get the value of W and B correct, we will be able to predict our new values. So with the help of gradient descent algorithm, model will find the values of W and B nearly close to our data points. Nearly close to our data point. Okay, try to focus on this point, this word nearly, because the model can only be accurate so far. It can never be 100% right, but you can make the accuracy, let's say 80% or 90%. So if your accuracy is 80 and 90%, most likely what you are saying is true. So with the help of gradient descent algorithm, our model will be able to find the values of W and B, the parameters of value. Okay. Now in order to implement linear regression, the first key step is to define cost function. Okay. We want to implement linear regression, but the first step is the cost function. Okay. Now
Okay.
what is cost function? Now we want to find out what is cost function. Okay. A cost function or loss function, in other words it called as loss function as well. A cost function or loss function will tell us how well the model is doing, so that we can try to get it do it better. What is it? The prediction. So with what the cost function will tell us that the how well the model is doing. Okay, it is basically the accuracy of the model. What is the accuracy of the model? What is the loss of the model? So let's say I'm testing the model with my testing data set. I have created this model. Okay. Now I'm testing it on the new data set. So let's say there are 1,000 examples that it will predict. Out of 1,000 example, it was able to predict 900 examples well and 100 examples wrong. I'm oversimplifying it, but let's say in the test data set, it was predicting 1,000 values. And I know what is the right value of that. So I'm comparing those values, the model prediction and that's why it is called test data set. The model prediction and the actual value. And what I find out is that it was able to predict 900 values correct and 100 values wrong. So what will be the accuracy of the model? 90%. And what is the loss of the model in terms of percentage? 10%. 10% loss is there. Correct? Am I making sense, Simran?
Yeah.
Yeah. So recall that you have a training set that contains input features and output target y. And the model you are going to use to fit this training set is this linear function, right? We are creating this linear function. Here, W and B are called parameters of the model, also known as coefficients or weights. Let's understand what these W and B parameters do. We are just trying to understand what this W and B, since if someone is coming from non-mathematical background, they want to understand what is the significance of W and B. So let's say W is 0 and B 1.5. If W is 0 and B is 1.5, the line will look like this. Why? Because model will always predict the value 1.5 based on this equation. We are using this equation. We are producing the function, na? So we are basically multiplying input, whatever input we are giving with the 0, and what we are getting is 1.5. That's why the line is straight line, horizontal line. So with W is equals to 0 and B is equals to 1.5, the line will be like this. Straight line, horizontal line. No matter what input we'll give, the model will always output 1.5. Now let's make B 0 and W 0.5. Now what will happen? The line will look like this. Here B is 0. B is 0 mane y intercept. The line is crossing where the line is crossing in the y where the function is this line, this linear line, this straight line is crossing on the y axis. So if b is equals to 0, so here the b is equals to 1.5, yani ki y line is crossing at y is equals to 1.5. This is 1.5, 1.5. So line is crossing at 1.5. That is called b. You can see this is 1.5. This is y intercept. Y intercept. Are you getting what I am trying to tell you? This is b, 1 and 0.5. This is 1.5. Okay. And if b is equals to 0, the line will cross the origin because it is intersecting the y axis at origin only. That is why the b is equals to 0. We are just taking an example to understand the W and B relationships, how it will manipulate the line, how the line will do, right? So we first make the W 0, the line will look like this, the horizontal line. And if we make the B 0, it will cross the origin. And with W is equals to 0.5, mane the slope of the line is 0.5. What does it mean by 0.5 slope? So with every increment of 1, there will be 0.5 increment of y. With every increment of 1 on x-axis, there will be increment of 0.5 on the y-axis. This is the meaning of slope. And slope it can also be calculated using tan x, tan theta. We are going back to the trigonometry again. What is the tan theta? Sin theta upon में cos theta. What is sin theta? In the right angle triangle, what is sin theta? Sin theta is equals to में perpendicular upon में hypotenuse. This is the angle. Sin theta is equals to my length of the perpendicular divided by the length of the hypotenuse. This is the sin theta. What is cos theta? Cos theta is equals to my base upon my hypotenuse. Length of the base divided by the length of the hypotenuse. And what is tan theta? Is the sine theta upon my cos theta. So that is what we call the slope as well. Okay. Now recall that you have a training set, or in simpler terms, that slope is the angle of the line. If you increase the slope, the line will move towards y-axis. If you decrease the slope, the line will move towards x-axis. Are you imagining what I am trying to tell you, Simran?
Yeah, I'm trying to understand.
Ha. So if I increase the angle, let's say there is a certain angle of this line with the x-axis. There is an angle. You can imagine the angle between the line and the x-axis, correct? There is an angle.
Yeah.
Yeah. So if I increase the angle, that means I am increasing the slope. If I am decreasing the angle, that means I am decreasing the slope.
So, yeah.
Okay, fine.
Yeah.
Okay. Now recall that you have a training set, and with linear regression, what you want to do is to choose values for the parameters w and b, so that the straight line you get from the function f somehow fits the data, well. Are you getting? For example, this is the training data set. These are the data points, right? These crosses are the data points, and this is my function fwb.
Yeah.
And what is xi, these are just denoting the ith example of the training set.
Yeah.
x0 y0 is the first row, or the first training data point. x1 y1 is the second data point, and x and yn is the last data point. And we are trying to create this line, this function, so that it will fit the data well. Now for a given input
I have,
yeah,
sorry,
please.
I have one question.
Please.
In last data, we have used two values, but I think here we are using more values.
When we are developing the algorithm, we
Yeah.
will only use that. Now we are just
Okay.
trying to understand what we are just trying. Don't confuse that we are going to use more data points. We will use only two data points. But here we are just trying to understand. Okay, this is just an example. What we are trying to understand? We are trying to understand the cost function. Right? Why we are trying to understand the cost function? To implement the linear regression. Right? So this is just an example. This is just an example. We will only use those two data points only. This is just an example to illustrate the cost function. What is the cost function? We are trying to understand the loss function or the cost function. So if I go back to our this line, when we just take an example of w is equals to my 100 and b is equals to my 100, you can see there is a huge difference between the data points and the line that we have created, or the model that we have created. That means the parameters were wrong. That means the loss is high. There is a great loss in this function, correct? And here the loss is 0 because the line is fitting the data well. Here the loss is high and here the loss is 0. Are you able to correlate?
Yeah, I'm understanding now. I thought you are using same data, so that's why I'm asking question.
No. Ask question. Asking question is the only way to get through. Otherwise, there is no point. When you ask me the question, then only I also able to explain it better. Or maybe I will find out something good that I don't know. Then we'll figure out together. Correct.
Yeah, because I'm thinking the first example is the outliers, and whatever the second example, the fit data is kind, we can say that it's the overfit.
Hmm.
Yeah,
Yeah.
it looks like the overfit, that it's not a perfect model.
I know, Simran, that you are also studying in the background. I know very well. Okay. But here we are not going to use any terminology. What we are going to use, we will define it. Okay,
Okay, okay.
I have not defined what is the overfitting and the underfitting. We have only used the two terminologies. What is linear regression, and
Sorry, sorry.
thereafter we have defined this gradient descent, and now we are understanding the cost function. Okay,
Yeah, loss function.
cost function and
You
loss
must
function.
you must write down in bracket also the loss function so nobody confused in
Sure,
this
sure,
thing.
sure, sure.
Yeah.
That is a
Hmm.
good suggestion of loss function. Okay. So, recall that you have a training set with linear regression. What you want to do is to choose values for the parameters w and b so that the straight line you get from the function somehow fits the data well, like this. This is fitting the data well. Can you see why it is fitting the data well? Because, okay, here comes, now we are starting the maths part. Okay, just focus, Simran, and my other viewers. Okay, why it is fitting the data well? If we take this example, let's say how many data points are there? 1, 2, 3, 4, 5, 6. 6 data points are there. And this function, I'm telling you that it is fitting data somewhat well. Not the 100% accuracy, but somewhat well. Why? Because it is very close to the data points. If you see the difference, okay, how are we going to know that how it is fitting the data well? Now for a given input xi, let's say this one, the function f also makes a predictive value of y, that is y hat. Let's say this is the data point xi and yi. So for the xi, the actual value is yi. Correct? Correct, Simran?
Yeah.
For the xi, the actual value is yi. But if I
Yeah.
but if I use this function fwb, it will give the output y hat I.
Yeah. It's a predicted value.
So there is a difference between y hat I and yi. You can see there is a difference between y hat I and the yi. Yani ki there is a difference between the predicted value and the actual value. Correct? There is a difference, no? Correct.
Yeah.
So to measure how well a line fits the training data, to do that, we are going to construct a cost function. The cost function takes the prediction y hat and compares it to the target y by taking y hat minus yi. This difference is called error. Now take the square of this error. Y hat I minus yi ka whole square. Now also we want to compute this term for different training example I. Now this is just for the one example, but what we want to compute is, we want to compute this term for the exam, for all the training examples. For that, let's sum up the squared errors like this. Sigma 1 to m. What is m? M is the number of training examples. We'll take all training example. What we'll do is, we will square the difference between the predicted value and the actual value, and we'll sum it up. We will sum it up. and after that we'll take the average of it, यानी कि we'll divide it by m only or 1 by 2m. This will what we'll call as average square error. To build a cost function that doesn't automatically get bigger as the training size and as the training set size get bigger by convention, we will compute the average squared error instead of total squared error. Okay, we are summing
Yeah.
up, we are summing up the difference, right? We are summing up the difference, correct? And we are taking the average of it. Now here comes the cost function, JWB. This is our cost function, JWB. We are defining it as J, just the way we have defined the function, our model function, as F. This is our cost function, JWB. This is the mathematical formula of the cost function. 1 by 2m sigma of 1 to m ब्रैकेट में y hat I minus yi का whole square. This is called squared error cost function. In machine learning, different people will use different cost function for different applications, but the squared error cost function is by far the most commonly used one for linear regression. This is our cost function. Can you mathematically think why this will tell us the loss of our model through this cell? Are you able to understand? Are you able to get the
Yeah.
mathematical intuition, right? We are taking the difference, then we are squaring the difference, and then we are taking the square difference of all the training examples, here the difference is 0, here there is some difference, here the difference is 0, here some difference, both little difference, here there is some difference, here there is some difference, and we are taking the sum of all of the training examples, right? So that's how we will know that our function fits the data well or not. We are taking the difference, right, from the model, right? And we are taking the average of it. That is our cost function or loss function. So also as y hat I, you know what is y hat I in this JWB? In this JWB, you know what is y hat I? Can you tell, Simran? What is y hat I?
It's the predicted value.
It is the predicted value. Correct. It is the predicted value. And how are we predicting it? Through this function, right? FWB.
Yeah. Yeah. We are predicting this
FWB
value
of
from
xi.
first of all from linear is a function.
Yes, exactly. Very good, Simran. And so that we can write this equation JWB as 1 by 2m sigma 1 to m ब्रैकेट में FWB of xi minus yi का whole square. Right. So loss is a okay, I'll run this cell again. This is all the markdown cells. Okay, we are not running running the code yet. We are understanding the mathematical part of it, and then we'll implement this function. Okay, now loss is a numerical metric that describes how wrong a model predictions are. Correct? Loss measures the distance between the model predictions and the actual labels. Correct? Here your terminology came, what you were saying, labels. Okay.
Yeah.
Are you happy now, Simran?
Yeah.
Okay, fine. So now the goal of the training a model is actually minimizing the loss. Now the goal has changed again. See? Now the goal has changed. What was the goal before? To predict the value. Let's come from the beginning. The goal was to predict the value. And then what was the goal? To get the value of
Minimizing
WB.
the loss.
No. After that, the goal has changed to the get the values of w and b, the parameters of function, right? The goal has changed to the finding of the value of w and b. To get the prediction, we need to get the w and b value, right? For the function.
Yeah.
The goal has changed to the value of w and b. Now, the goal of training a model is actually minimizing the loss, correct? And reducing it to the lowest possible value, correct? This is our goal now, to minimize the loss, correct? We'll keep finding the values of w and b until we get the lowest possible loss. And what will be the lowest possible loss? 0. I want to find 0. At least, matlab, optimistically I'm saying, realistically it's not possible, but at least let's say 1%, 2% loss. I want to bring it down to the 1%, 2% loss, correct? Now, are we together on till this point, Simran?
Yeah.
We are on
I'm
the same page,
understanding
na?
now.
So far the understanding is on the same page, right? Now,
Yeah.
there are some certain types of losses. In linear regression, there are 4 main types of losses: L1 loss, L2 loss, mean absolute error, mean squared error. Mean squared error you just learned. This is called L2 loss, right? 1 by n sigma of actual value minus predicted value का whole square. This is called mean squared error, MSE. Okay. What is the L1 loss? Sigma of actual value minus predicted value. And this is the what do we say? This is the mod actually. You can see there is a bar, right? Between the actual value minus predicted value, there is before A and after E there is a bar. So bar means whatever the value comes, it will give some positive value. Yani ki we are only concerned about the difference. Whether it is negative or positive, we don't care. We are concerned about the difference. What do I mean by that? Whether the y hat I comes down, lower, or the y hat I comes up, I don't care. I only care about the difference between y hat I and yi. Correct? If it
We
is,
can say that the
no.
difference between the
Yeah,
actual
yes,
value and the predicted
yes,
value.
yes. See, if model is giving lower value than the actual value, we will say underfit. And if model is giving the predicted value more than the actual value, we will say overfit. We do not want underfit or overfit. We want the fit. We want to minimize it. So that is why there is a bar between when we are summing up the losses. There is a bar. This is a mod function. That is why only we are squaring the value, right? And we are no, we are squaring the value for another reason, to to basically maximize the loss, to get the more accurate loss. When we are squaring, let's say I am getting 2, by squaring I'll get 4. If I minimize the 4, the 2 will be much more minimized. This is like mathematical. But why there is a bar? Why we are using the mod function? Because we are only concerned about the difference between the value of actual value and predicted value. So in L1 loss, it is the sum of the absolute value. This is what we call absolute values. We are not concerned about the real values. We are concerned about the absolute values of the difference between the predicted value and the actual value. This is called L1 loss. The sum of the absolute values of the difference between the predicted values and the actual values. Right? And what is
Yeah.
the mean absolute error? It is the average of L1 loss. We'll divide by n.
Yeah.
Now, what is the L2 loss? Now you can guess, right? L2 is the square. The sum of the square difference between the values.
Yeah. For example, we are for L1 loss, we are using like a graph, and one of we are using 25%, and the mean is the 50%, and L2 is the 75%, like this. And then another is the minimize and maximize.
No, sorry, I was not able to relate. Can you explain that again? What are you saying?
It's a chart. We can see that it's the mean, and another is the 21 L1 loss is the half part is taking the 25%, and the mean is the 50%, and another is the 75%, and another two values is the minimize or maximize. It's a formula like that to calculate these things.
Mm, 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 mm. What do you mean by 25 and 50? What do
It's it's a value of dividing into the mean mode, like that, and they are dividing the part in 25%, 50%, and the 75%.
Hmm.
We are using the maximum mean as well. I have one, maybe I will check it and I will send you if you want.
Okay, okay. But what I'm trying to tell you here is that we there are four type of losses that we use in linear regression. One is
Yeah.
L1 loss, and one is L1 loss, and the mean absolute error, the average of L1 loss, and there is another one L2 loss, and the mean squared error, which is the average of L2 loss. Okay.
Yeah.
So the function difference, you understand this point, right? Then only I will move forward if we are on the same page.
Yeah.
Okay, fine.
Yeah.
Okay. The function difference, the functional difference between L1 loss and L2 loss is squaring. When the difference between the prediction and label is large, the squaring makes the loss even larger. When the difference is small, the squaring makes the loss even smaller. Okay, yani ki less than 1. Okay. Now, as we know, the goal of the model is to minimize the cost function or loss function. The best way to find those values of W and B is applying the optimization algorithm called gradient descent. Now you can see, now we can talk about gradient descent. Now we understand how to know that the model is fitting the data well or not. How are we determining it? Through the loss function we are determining it. And what is the loss function? Let's say L2 loss we are considering. So it is the average of square differences between it is the average of sum of square difference between the actual values and the predicted values. That's how we will get to know that our model is fitting well or not. Not by judging visually. This is the visual, this is how we are judging it visually. Okay, the model is not well because it is not crossing the data. Because why? Because here we have only two data points. Let's say we have, in the real case scenario, it will be millions of data points. How we will determine that the model is fitting well or not? Through this loss function only. Through the loss function, we'll get to know that our model is fitting the data points well or not. And there are many different types of loss functions for every different types of machine learning models. But as we are only learning the linear regression, in linear regression, we have only four type of loss functions. One is L1 loss and L2 loss and there is mean absolute error and there is mean squared error. And so our goal is to minimize the loss function. Correct है ना सिमरन? Our goal is
Yeah.
to minimize the loss function. Correct है ना? And how we will determine?
Yeah.
Through the loss function. We'll get the value
Yeah.
of
We
loss
will.
function. We'll try to minimize it. And the
Yeah.
best way to find those values of W and B is by applying the optimization algorithm. So earlier we are guessing the values of W and B, right?
Yeah. Now we are using the gradient descent.
Now we are going to use the gradient descent. Okay. So gradient descent is a mathematical technique that iteratively finds the weights and bias that produce the model with the lowest loss. Just by with this line you will be able to know what this gradient descent is doing. I'll read this again. Gradient descent is a mathematical technique that iteratively finds weights and biases. Weights and bias iteratively, yani ki on every iteration it will give the weight and bias. This algorithm, when we run this algorithm, where we will run this algorithm? On our data set, on our training set. This is the part of our machine learning model, training the model, correct? So to find the values of weights and bias, we are using this gradient descent mathematical technique, and it will iteratively find the weights and bias. So for each iteration it will give us the values of W and B for every iteration, and it will iterate like 100, 200, 400, 900 iteration it will do until it will get to the lowest loss. It will automatically find. This is a mathematical technique. So are we clear on this line, or should I repeat it again? Simran?
Yeah. I can understand.
Okay. So gradient descent is a mathematical technique that iteratively finds the weights and bias that produce the model with the lowest loss. Now let's visualize what the gradient descent does. So we'll give the weights, some value of weights and bias. This is the first step. It will go to the model, it will get the prediction, determine the loss, right? It will have the loss. And how we'll get the loss? How we will get the loss? Through the loss function.
Yeah.
Yeah. And it will determine. Now this is the second step. This first step is calculate loss. Second step is determine the direction to move the weight and bias. So let's say weight is 100, bias is 100. Now it will determine, the algorithm will determine whether I should increase the value of W or decrease the value of W, and whether I should increase the value of B or decrease the value of B. It will determine the direction simultaneously. How it will determine the direction, that will we also study today, but it will determine the direction. And which direction it is moving towards? Towards the lowest loss. The goal of this algorithm is to get the lowest loss. So first step is to calculate the loss of the current weights and bias. Second step, determine the direction to move the weights and bias that reduce loss. तो जो पहले जो लॉस आया उससे मुझे कम लॉस चाहिए. I want lower loss than that. Now move the weights and bias value a small amount. मतलब बहुत ही थोड़ा. ऐसा नहीं मैं एक बार में I'll do like 100 के बाद सीधा मैंने 150 कर दिया ना. It will move like 100 के बाद it will move like 100.1 100.01, and bias it will move like 99.98. So it will move like that, very small amount, in the direction that reduce loss. And the fourth step is return to step 1. Again it will go to the step 1. Now we have the values of W and B. It has moved towards the direction to reduce the loss. Now it will go to the first step, and again it will do the same thing until the model can't reduce the loss. Matlab, model cannot reduce the loss anymore. This is the best it can do. Move the small amount in the direction, and then it will again repeat the process until the loss can't be reduced. This is the fourth step. Repeat the process until the loss can't be reduced. Okay?
I have one question related to gradient distribution. We can also select the steps also. For example, the value of alpha. Can we select it so we know the which direction our model are going on?
Direction it will decide, but at what rate you want to make this happen, this gradient descent, that you decide, which is called alpha, what you are referring to. So alpha is the hyperparameter.
We are giving the hyperparameter before we start.
Yes, correct. But algorithm will find the values of W and B itself. We'll just give the training data set. Model will find the values of W and B.
Okay, thank you.
Through this algorithm, gradient descent, which will eventually get the loss to the lowest possible. And to run this algorithm, we need that hyperparameters. We need those hyperparameters. What is the significance of this hyperparameters? That I will come in the next slides. We will come to that point. But is your doubt clear, or you want to ask more?
Yeah, it's clear.
Okay, fine. Now, gradient descent is used all over the place in machine learning and deep learning. Here is an overview of what we will do with the gradient descent. You have a cost function that you want to minimize, correct? Now, gradient descent is an algorithm that you can use to minimize any function. In this case, the cost function. Now, just to make this discussion on gradient descent more general, it turns out that gradient descent applies to more general functions, including other cost functions that work with a model that have more than 2 parameters. What I am trying to say is, here we have only 2 parameters, W and B, that we want. But this gradient descent algorithm is that much good that it will be able to perform the minimization of the function which have more than 2 parameters. It will work with that model as well. What do I mean by that? More than 2 parameters? I mean, here we are only considering x, w y hat is equals to में wx plus b, correct? Because we have only one input feature. But let's say you have 10 input features. In the real case scenario, there will be multiple dependent variables, right? In this example itself, the predicting of price of the house is not only dependent on the size of the house. It will be dependent on other variables as well, other input features as well. So with the help of this gradient descent algorithm, so what will be the function of that model. Let's think about this. What will be the function of that model? It will be somewhat like y hat is equals to me w1 plus x, w1 plus x1 plus w2 plus x2 plus w3 plus x3 plus w4 plus w4 x4 w1 x1 plus w2 x2 plus w3 x3 plus b. Correct? Are you getting what I am trying to tell you? With the multiple input features, there will be multiple w's. Let me come back to that formula again. This is our function, na? F wb of x is equals to wx plus b. Correct? Why? Because there is only one input feature x. But let's say there are multiple input features. Not let's say, in the real case scenario, there will be multiple input features. Correct? For every input feature, there will be a different w value. Correct? Or you can say the size of the house will affect more to the price, and the locality of the house or the number of the bedrooms will affect more or less. That will be the multiplication factor, right? That is the weight. So with every input feature there is a multiplication factor. Correct? That is the w value, that is the value of w, that is the weight. For every input feature there will be a different value of w. Correct? Can we agree on this point? With every input feature,
Yeah.
let's say if we have 10 input features, we will have 10 values of w. We want 10 values of w. Correct? Can we agree on this point?
Yeah.
So with so I can say with 10 input features, how many parameters do I need? 11. 10 w's and 1 b. Correct?
Yeah.
Okay, fine. Then we can move forward.
If we have 425 values, then we need a 426 parameters.
Correct. Four, no, not values. 425 features.
Right, 425 features plus B.
Ah, right. Then we will need 426 parameters. Then we'll need
That's why I'm
420.
asking.
You are asking, or are we clear on this?
I'm asking, so I'm maybe I'm understanding maybe wrong. That's why
Mm-hmm.
I'm repeating.
Mm-hmm.
Is it clear or not?
Mm-hmm. Please, please, yeah, please.
Yeah, that's why I'm asking. Okay, I'm
Mm-hmm.
taking maybe the 425 parameter value features,
Uh,
and I'm getting 425 parameters and plus B. It's the 426 total parameters.
correct.
I'm asking like that.
Correct. You said exactly right. You are absolutely correct on this point. If we have 425 features, यानी कि 425 dependent variables, we need 426 parameters. Now can we move forward?
Yeah.
Okay. So the cost function, just to make this discussion on gradient descent more general, it turns out that gradient descent applies to more general function, including the cost function that work with the model that have more than two parameters. That the case, right? So the cost function can be written in this way: j w1 w2 w3 w4 w5 b. The cost function will be written in this way. Earlier the cost function was written in which way? jwb, right? Where are the w and b used? W and b are used in this one, predicting values. Correct? Here the jw with the 5 parameters it will return is jw1, w2, w3, w4, w5b. And the objective of gradient descent is minimize, is to find the is to minimize with the values of w1, w2, w3, w4, w5 and b, which will minimize the value of this function. This is the objective. We are putting the minimum function onto this function. We are putting the minimum function onto this function, cost function. This is the objective of gradient descent, right? The objective of gradient descent is what? Repeat until the loss can't be reduced. Correct? This is the objective of gradient descent. The loss can't be reduced anymore. So
Yeah.
I'm writing it in the mathematical denotation. Minimize this function with the values w1, w2, w3, which will minimize the function of j. In other words, you want to get the values of w1, w3, w4, w5 and b that give the lowest possible value of j. Right? Can we agree on this cell? Can we move forward, Simran? If we agree on this cell, then we
Yeah.
have to move forward. Otherwise, no point.
No, I think we will move forward.
Okay, fine. Then here is model convergence and loss curve. If you see, okay, the gradient descent will iteratively gives the values of w and b, right? Here is some example. It is just an example how the gradient descent works. Initially, on the zeroth iteration, the loss is 400, and it will slowly, the iterations, let's say on the 200th iteration, the loss is already at the 90. Earlier it was at 400. Now on the 200 iteration it has reached to the 90. You can see, right? We are moving the x direction. The iterations are here. On the 200th iteration the loss is 100. Why? Because that's how the gradient descent algorithm works. It minimizes the loss. It moves towards the direction where the loss is minimum than the previous value of w and b, with a very small step it takes. So dhire dhire it will take. After the 100th iteration it will start converging. 100th iteration tak it is very slowly it is going down. Oh sorry, not 100th iteration, I'm sorry. On the first iteration it is this. Let's say on the 100th is here, 100th iteration it has already reached to the 90% loss or 900 loss or 90 loss. On the 200th iteration it is somewhere at 80, let's say. On the 400 iteration, which iteration are we talking about? We are talking about this iteration. This is the step that we are doing, right? On the 400th iteration it is giving like 30. On the 600th iteration it is what? 20. On the 1000 iteration it is nearly 0, right? This is the goal of this algorithm, lowest possible value. That's how it works. You can see that loss dramatically decreases during the first few iterations, then gradually decreases before flattening out around the 1000 iteration. We can be mostly certain, okay, yes, okay, you can see that, okay, we can be mostly certain that the model has converged. This is what we call the convergence of the model. The model has converged. What do you mean by convergence? The loss is almost 0. In the following figure, if we draw the model at 3 points during the training process, on the training 1, on the first iteration, the loss is this. ठीक है, on the first iteration, this is the first iteration, this black dot is the first iteration, correct? And if we plot our
I
model,
have
huh,
I
sorry,
have one. Can I ask you one question?
please.
Um,
Hmm.
can we get the loss also the negative value?
No, loss will always be some positive value. Why? Because we are using mean squared error, and in the mean squared error we are squaring the difference of the values, actual value and the predicting value. We are squaring the difference and then taking the average. So when we square the negative value, it will be a positive value, correct? if you
Yeah.
if you square minus 2, square minus 2, what will be the value of minus 2 square? It will be 4. Minus 2 multiplied by minus 2 is 4, right? So we are squaring the values, the difference we are squaring, we are squaring the difference. That's why the loss cannot be negative. Are you getting? Loss can never be
Yeah. Thank
negative.
you.
Yeah. Yeah, are we on, are you getting, is your question answered?
Yeah, I'm getting. Yeah, really, it's nice. You are clearing very well.
Also in the L1 loss, where we are not squaring, we are taking the absolute values. If you can see, there is, that's what I was referring to. Before A there is a bar, and after E there is a bar. We are only concerned about the value of the difference. We are only concerned about the absolute values. We are concerned about the absolute values. What is the difference between the actual value and the predicted value? We are not concerned about, right now we are not concerned about whether the model is giving the lesser value or the, or more value than the actual value. We are only concerned about the difference. In the L1 loss also we will not get the negative value. In any of the loss we will never get the negative value. Okay. Okay. Can we agree on this? Is your answer question, is your question answered? Simran, do, so here, so here on the first iteration, if I plot my model, I am plotting my model with the data points. You can see there is a difference between the actual value and the predicted value. This line, this blue line. So, ah, so here on the first iteration, I am plotting my model. On the, why, how am I plotting the model? On the first iteration, it will give me the value of W and B. Correct? That's how the gradient descent work. On every iteration, it will give the value of W and B. And I'm plotting my function with the value of W and B. So this black line is representing my model on the first iteration. This black line is representing my model. And this blue line is representing the loss line. Obviously, the red dots are the data point, but these blue lines are the loss lines. What do I mean by loss line? The difference between the actual value and the predicted value. I don't care whether the model is giving more value or lesser value. I only care about what is the difference between the actual value and the predicted value. Through that, I will calculate the loss. So in this example, on the first iteration, the loss is very high. You can see lot of blue lines, correct? On the 400 iteration, if I plot my model, you can see very less blue lines. That means the loss has reduced. And in the 1000 iteration, you can see very few blue lines. That means the model has converged. Are you there, Simran? Are you listening? Are we on the same page yet?
Yeah.
Now, let's understand this gradient descent visually. Now, we are starting with some value w and b. Let's say w is equals to 0 and b is equals to 0. Keep changing the w and b to reduce jwb until we set at the at until we settle at or near a minimum of this. Simran, I'll just be right back in 1 minute, okay? Okay, just give me 1 minute.
I have question, Himanshu. How many hours we will take this class?
Until we understand the linear regression, I'll continue. If you want to drop, you can drop. I'll continue. I'll record this. Assuming you are
Okay,
here.
okay,
I will
okay.
assume Simran is studying with me. It is okay. If you want, I know there are other priorities. If you want to go, you can leave. That is fine. I will record this whole sentence, this whole session until the model predicts my value of W and B, which will fit my data well. I will not stop.
Okay,
I will
okay,
not stop
okay.
until it will give me the value of W and B automatically, and I do not have to guess.
Okay,
Correct?
okay.
Uh, Actually, I have also another meeting. I'm just pinging my friend over. Okay, it will take me more time. I thought it will be over in 1 or something hours, but it took more than I expected. But it's okay. The more question we answer, the better quality content I am creating. When somebody will come to this video, he will be able to understand linear regression pretty well after watching this video.
Yeah, definitely. Really, it's nice.
Right? Okay, so let's understand this gradient descent visually, then we will go towards the mathematical part. Okay, so far we understood how it is going to do. Now gradient descent is a mathematical technique to reduce a function until reach convergence. Now we can understand what is convergence. Convergence means lowest possible value of cost loss function. Okay. Now, in terms of linear regression, gradient descent is a technique to find weights and bias of a cost function that gives the lowest possible value. In terms of linear regression, gradient descent is a technique to find weights and bias of a cost function that gives the lowest possible value. Right? Gradient descent will give us the value of W and B, which will give the minimum value of the loss function. Now let's start W and B with 0, 0. We are taking 0 and 0. Keep changing the W and B to reduce JWB until we settle at or near a minimum. Now this is what we call local minimum. If you are not aware of mathematical, let me revise you some concept of local minimum. Let's say this is a function. You know, this is a function. This on xy graph, this is a function. This u is actually a function. Just like our model is a straight line, this is a function. We can represent any curve with the help of a mathematical equation. There is a parabolic equation, there is a sinusoidal equation, right? There are any curve we can define using the mathematical equation. So let's say this is a function. and it is plotted on xy graph. I'm not talking about j, I'm just revising your concept of local minimum. What do I mean by minimum? So let's say this is a function, and what is the highest possible value that I get through this function? This one. Why? Because it is reaching the y axis to the highest point here. This is the highest value. And what is the lowest value of this function? This one, this point, right? Y value of this point is the lowest. So this is the local. This is the minimum value of this function. This is the highest value. This is the lowest value. Well, let's say if this is the function j, I want to reach here. Okay. Now have some function jwb. What do I mean by wb? J is a function which is dependent on w and b. Can we agree on this? For linear regression or any function, we want to minimize jwb. w1, w2, wn till b. We want to minimize w1, w2, wn till b. We want to minimize of jwb. Right? Outline. Start with some wb, w0, comma b, w comma 0 and b comma 0. Let's start with some point, so we need to start na. So we'll start with 0 comma 0. We'll take w also 0 and b also 0. And what we will do with that 0 comma 0? What we will do with that, Simran? We'll calculate the loss, right? Now if I go back to our gradient descent algorithm, we'll calculate the loss. After calculating the loss, we'll determine the direction to move the weights and bias. Let's say with w is equal to 0 and b is w is equal to 0 and b is equal to 0, the loss is very high. You know, the loss is 400. With w is equal to 0 and b is equal to 0, loss is very high. Okay. Now what I want to do, I want to move, no, not I, the gradient descent algorithm wants to do, it wants to move towards the direction of weights and bias where the loss will be reduced. It will take a small step in the step 3. It will take the small step. Now it will update the values of w and b with those small steps, right? Until it reaches the 0. Now visually, let's make let's take a now let's take a look at example of more complex surface plot of j. This is the j. This is a 3D plot. Why 3D plot we are considering? Because we are considering w and b. This is the value of w, this is the value of b. So if I am like at this point, this is a 3D plot, you can see, right? This is a 3D plot. So in this 3D plot, let's say I'm point at at this red point. The red point is the loss highest and the blue point is the lowest. Z axis defines the loss, x axis defines the w, and y axis defines the b, and the z axis defining the loss j. So let's say I'm at the red point where the loss is high. At the red point, there is a certain value of b, w and b, and the loss is obviously the high. We are at the highest point. At the middle, there is 0. And bottom, there is negative value. There are negative value as well. You can see, right? Z axis divided in the middle, there is 0. The green is 0. Green is 0. Red is high, red is positive value, and blue is the negative value. Now you were asking na ki the value can be negative or not. You have asked this question, right? The value can be negative or not. to answer your question, the value of the loss function can be negative, but it cannot be mean squared error that we are using. Okay, but for the understanding, let's say blue part is the lowest possible point that we want to reach. This dark blue is the lowest point. Okay, so let's say we are at this point, a guy. Now imagine on this is a hill of, this is a plane of cost loss function. I am at the top of the hill where the loss function is high. Now what I will do, I am at this point. What I will do, I will take 360 degree turn and see to which direction I should move so that I will go lower. So I'll take this direction. Then again this point, again at this point I will take 360 degree. Then I'll see, okay, this direction. Then again at this point I'll take 360 degree. Then I'll take this direction. Then again here I'll take 360 degree turn. Then I'll go this direction. That's how taking small step until it reaches the convergence, where it cannot go beyond the lowest possible value. This is the lowest possible value of j. That's how it is taking the value of w and b. It is taking the 360 degree turn. It is considering all the possible values of w and b at this point, and it will consider the values through which it will get the, maybe it will take this path, maybe it will take this path, but eventually it will reach here. Are you getting?
Yeah.
Maybe it will take this path, maybe it will take this path, but eventually it will reach here. It is considering at every point, it is considering all of the points. How? I will tell you.
It means ki we can take the minus traction as well. If we are in top, then we come back, then we will take the minus traction, right?
Minus step, you mean go back?
Yes.
We will never go back, because going back means we are considering the value where the loss is high. Are you saying that?
Yeah. No. I'm thinking about it. We are in top of the hill. We are
Uh,
going down.
uh,
So that I'm saying we are going from down direction.
down direction. Yes, yes. Uh, yes.
That's why I'm asking the question: ki is it negative value can possible, or how we can select the direction, or it's the algorithm will select it
I'm telling you,
themselves.
na, like visually I'm telling you, mathematically we will come, okay? But visually I'm telling you, at every point, the algorithm will consider all the points of W and B. That is what it means by 360 degree of this guy. When I am saying 360 degree, it is basically considering all the values of W and B at this point. At this point, what are all the values? At this, you can say for the small amount, it can only take so far, na? Around this point, let's say this is the line. Let's create this line around this point. How many values of W and B? So it will consider all the values, and whichever the value is giving the lowest j, it will take that value. Then it will go down, and at this point it will again consider all the values around it. So if it goes back, the value will be, the j will be high. If it goes here, the j value will be less, so it will take this path. Are you seeing? That's how that's the beauty of mathematics here. It is considering all the values.
Yeah.
Are you getting like what I'm trying to tell you? It is considering all the values. The 360-degree means
Yeah.
it is considering all the values of W and B. All the
Yeah, I considered they are going step by step.
all the possible values of all the permutation combination of W and B simultaneously. It is considering. See, to calculate these many calculations simultaneously, you will require a lot of compute, and for that we are using numpy. That's why we are using numpy. If we do it using the normal for loop, it will take forever. With the help of numpy, we are able to perform these calculations fast. At every point it is calculating it is considering everything. Basically all the possible values of W and B. How? I will tell you. That's where we are going next. So eventually it will reach to a convergence. Okay, fine. So this is called, okay, this is called the global minimum. This is called the global minimum. And these blue points, which you can, other blue points also you can see, right? It can go there as well. Correct? These are called local minimum. It can reach here as well. It can reach here as well. But it reached here, which is the global minimum. It can reach to a local minimum. It can reach to a global minimum. Oh, sorry guys. Okay. Uh, okay. Now, mathematical implementation of gradient descent. On each step, now you need to focus, Simran. Now, don't lose the focus because we have run so far. This is where the main part comes. Okay. Now, mathematical implementation of gradient descent. On each step, we calculate the weights and bias. I'm telling you, na, every point it is calculating the weights and bias. How it is calculating? W is equals to me W minus W is equals to me W minus W is equals to me W यानी कि current W is equals to me W minus alpha dy में dw of jwb. Again I am repeating, W is equals to me W minus alpha multiply by dy में dw of jwb. What do I mean by dy by dw? It is a partial differentiation of function jwb. So function jwb, it is a function of two variables w and b. I am partially differentiating this function with respect to w. Now there comes the mathematical concept of partial differentiation. Okay. So w is equals to me w minus alpha multiply by में dy में dw of jwb. What is alpha? Alpha is the hyperparameter. This we will provide. What it will do? It will take the it will tell the speed. I'll tell you. It will come. Okay. And what is d by my dw of jwb? Small steps on loss curve or derivative. It is the derivative of jwb. Okay. Similarly, it is also calculating b. B is equals to b minus alpha dy by db of jwb. Okay. And you do it repeat and simultaneously until the algorithm converges. Means you reach the point at local minimum. What do I mean by local minimum? This is the local minimum. Okay. The point where I want to reach, where the loss is the lowest. Now, where the parameters w and b no longer change, where the parameters w and b no longer change much with the additional step. The sense now let's talk about the sense of simultaneous update. It will update, right? We are calculating the value of w and we are calculating the value of b, and we are simultaneously calculating these values because we want to work with the values w and b until the algorithm converges. So what do I mean by that? I mean temp w is equals to w minus alpha d by dw of jwb, and temp b is equals to b minus alpha d by db of jwb. Now w is equals to temp w and b is equals to temp b. Now simultaneously we will update the values of w and b. What do I mean by that simultaneously? Let's say at this point at the top of the hill, I calculate the value of w where I will get the minimum convergence. I have calculated the value of w with the help of this formula. Right? And I also calculate the value of b as well. So what I will do is, why we are doing the simultaneous value? Because we are updating the value of w every time. So w is equals to w minus alpha d by dw of jwb, and b is equals to b minus alpha d by db of jwb. As you can see in this formula itself, the w is using again. So what I will do is, I will create some temp w. Temp w is equals to w minus alpha d by dw of jwb, and temp b is equals to b minus alpha d by db of jwb. Here the w is same. Thereafter I will update the value of w and b. What I got? What will be the incorrect update? I got the value of temp w and then I will update the value of w. Then it will affect this step where I am calculating the value of temp b, right? Because in the jwb we are also using w, correct? That's why we are using simultaneous update. First we will calculate the temp w, then we will calculate the temp b, then we will update w and b. Now gradient descent summary. What is learning rate and derivative doing? And second, why multiplied together like this it results in update to parameters w and b. Right? Two things are here: learning rate and derivative, and something called simultaneous update are also there. So जब ये एक दूसरे से मल्टीप्लाई करता हूं मैं, यानी कि लर्निंग रेट को डेरिवेटिव से मल्टीप्लाई करता हूं, तो हाउ एम आई गेटिंग दिस लोएस्ट वैल्यू, the direction where I want to go, how it is happening? This is the question. For simplicity, we'll work on the minimizing just one parameter. So far we have developed a linear model that predicts fwb of xi. Fwb of xi is equals to wxi plus b. In linear regression, we utilize input training data to fit the parameters w and b. By minimizing a measure of the error between the predictions by FWB and the actual data yi. Correct? FWB of xi and the actual data yi. Correct? The measure is called cost, JWB. Correct? In training, you measure the cost over all of a training example xi and yi. Correct? And the gradient descent was described as repeated until convergence of this. W is equal to W minus alpha d by dw of JWB, and B is equal to B minus alpha d by dw of JWB, where the parameters W and B are updated simultaneously. Therefore, the gradient d by dw of JWB is defined as, this is the actual formula. It is FWB of xi, the summation of 0 to m divided by 1 by m, FWB of xi minus yi multiply by xi. This is the partial derivative of w. And what is the partial derivative of b? 1 by m, 0 to m minus 1, FWB of xi minus yi. How we have reached to this formula? How this derivative converted to this formula, I am also not aware of. I will get to that part later, but it will eventually be like this. There is particular research. There is some mathematical derivation that belongs to the derivation. We will derivate this JWB. We have the function JWB like this. If we derivate this function using W, we will get this. There is some derivation behind this, but after that derivation we will get this. And about the how part, that how it is, so we are considering the derivative of the function. We are differentiating of this function with respect to W, and then we are differentiating this function with respect to B, multiply by the alpha and a learning rate, and we are updating the value simultaneously. By derivating, what does it mean? What do you mean by derivating the function? We are reducing it. We are taking the small step. And how it is going to the convergence? It will check the values of W and B. It will check the values of W and B and calculate the loss. And if the loss is greater than the previous one, it will not consider. If the loss is less, it will consider, and then it will move forward. That's how it will do it. Now let's implement the gradient descent. Now we have the formula. Now we can simply use Now we can implement the gradient descent. Why are we implementing the gradient descent? To get our values of W and B. We'll need to implement gradient descent algorithm for one feature. For that we need three functions: compute gradient, compute cost, and gradient descent. What is compute gradient? Compute gradient will do this part. Compute gradient will compute this part, because every step it needs to compute. On every step it will compute. So we need a function that will compute on every step, right? This part. So as you can see, for this part, for this function, what do I need? We need the function fwb, yi and xi. As you can see, I have the function fwb. I'll compute the gradient. This is the gradient function I am implementing, right? This is a compute gradient function. In this function, I have input feature x, I have target values, and I have wb model parameters. And what it will return? It will return the derivative, some scalar value of dj by my dw and dj by my dv. Two derivatives it will return. Right? After that, I will use the compute cost as well. This is the function where I am computing the cost. As you can see, I have only implemented the function, and here I am using numpy library, right? np.sum. These are the function that I am using. And what I am doing, I am only using this functions that I have just explained to you, right? So in this compute cost, I am computing the cost of our model, and it is the part of the gradient descent algorithm. Now this is the gradient descent algorithm. In this algorithm, I am computing the cost, and what it will return? It will return the, what it will take? It will take these many parameters. How many number of x and y? Okay, the input feature and output targets, training data set, w initial value and b initial value also need. Okay, alpha is the learning rate. Okay, it is a float value that we need to give. And then number of iterations, how many iterations I want to perform. And then compute cost. This is the function that I'm providing to this gradient descent function. I'm providing this function because it needs this function, right? Where it will need it? On every iteration it needs, na? On every iteration it needs, na? So I'm providing this function and compute gradient as well. It needs compute gradient as well. So here if you can see, I'm looping through the iteration. Here I'm getting the gradient on the, let's say on the first iteration. Here I'm initializing the value of b in, b, w in, okay? And here I am updating the parameters, the simultaneous. Now here I am saving the cost of j function on some j history, just to, just to keep the cost, right? Here I am using the cost function. Okay, and I am printing the cost at every 10 interval of 10 times. On every 10th interval I am printing the cost. This is the code for printing the cost. That's it. And it will return the value of w and b, j history. J history means cost history, and p history. What is the p history? P history is the value of w and b that it predicted, that it went through. It will keep updating the values w and b, na? So it will give that value. Now let's run this function. Here again I am running this function, right? Okay, now to run this function, what I will do, I will just, okay, now again it is connecting. Since we are not running any cell, it disconnects. Okay, maybe it will throw an error because we have not okay, now it, no, it is not creating. Okay, fine. Here is my final code. Okay. See, gradient descent has find the value of 194 and 088. It has find the values of W and B automatically. If you can see, initially the loss is very high. On the 0th iteration, the cost is very high. But it has finally reached to the, it has given me the value where the cost is very low. This is the lowest value that it can reach. Through this, it will be able to predict the value of W and B. Now, if I use these values onto my function will look like this. You can see. So I have got the values, right? I have got my model, correct. Now through this model, there is very minimum loss, right? So that is our linear regression model using numpy. The code is very less. Code is not that great. Code is not, lot of lines are there. That's the beauty of Python. Inside this, there are some np.dots that we are doing, dot product we are doing, some product we are doing. But the mathematics is what doing the main part. Through mathematics, we are able to get the values of W and B. Now we can increase the data points and we can still train the model and it will give us the right values through with the help of gradient descent. So that is how we implement, that is how the linear regression model is implemented in the scikit-learn using this methodology only. Maybe some other advancement were there, but the core idea is this. So thank you again, guys. Thank you for joining. Thank you for joining this session, and thank you for watching me this long and bearing my voice and my bad teaching skills. I just tried to explain what I learned, and next time I'll explain some other algorithm that I will find, and we'll learn that as well. And if I have said anything wrong or anything wrong information that I have provided, any incomplete information that I have provided, you can paste it on the comments. I will be happier to answer your queries. And yeah, thank you again. Thank you guys.